Hello everyone, welcome back to Physical Geology 1403. I'm going to turn these lights off at the front so you can see that screen better. Today is lecture 3. We are learning about igneous rocks and intrusive activity. We are joined by my two teaching assistants today. First up, Chloe. This is Chloe Oren. She's been my TA this is your second semester as my TA. She took the class from me last year. Did very well, latched on very well to the topics, so she was a natural fit as a TA. So if you guys need any assistance with tutoring, or if I need to leave for a few minutes and come back, she's kind of the go-to. I am also available at some points for tutoring if Chloe is not. Do you know if the other TA is still TAing? Sue. She is? Okay, so we also have another TA over at the LRC, because the LRC is back open again, I think, named Sue Claypool. She is a TA available. So if you need any time with any of the TAs, please go to the LRC website, reserve some tutoring time with them there. This also works for my online students as well. That is something available to you as well, to come here in person, or sometimes TAs will have virtual opportunities available. I don't know if Chloe has done any of those. I know that in the past, Sue has done some virtual tutoring as well. I also am available to do that depending on the time that you can work with. Okay, the other teaching assistant I have is around my neck. This is Diablo. The first time he's joining us. He was shedding last week. He is currently in what is called torpor, which means that he's not very active. Normally he would be kind of slithering all over me, kind of exploring, trying to find a way off of me, because I'm essentially a tree for him right now, a weird talking tree. But torpor is basically when they enter a few months of pseudo-hibernation, where they suspend their metabolism, because during the months of winter, all of the prey that they would normally be hunting is hibernating, right? All the small mammalian rodent prey that they would normally eat, they are hibernating during the winter. So snakes and other predatory reptiles will enter torpor until their prey comes back out. So he's still in that. So he's going to be kind of lackadaisical today. Give it a couple of months once I start feeding him again, and he'll be right back at it. He is a ball python. I love using ball pythons as teaching aids, especially in this class. They're kind of cool, but in 1404, where we learn about evolution and the history of life and genetic traits and things like that, they are really cool examples to teach with, because their coloration, the patterns on their skin, those are all genetically inherited. So very, very useful there. Okay, so his name is Diablo. If you haven't been to the zoo next door, I have a couple of turtles, another snake named Medusa, and a lizard over there as well. And for any of my online students, you're more than welcome to come on campus and meet any of these animals anytime you like. Okay. Let's start off by opening the floor to any questions you might have about last week. You got 2 lectures last week. On Tuesday, we learned about, we just kind of got a general introduction to geology. And then on Thursday, we learned about matter and minerals, how atoms come together to form bonds. Those bonds make networks, frameworks, crystalline frameworks, which grow into minerals, and those minerals in turn make rocks. Today we're going to talk about our first type of rock, igneous rock. But before we do, any questions that you've thought about since last week? Or any cool stories, scientific or otherwise, you want to share? Oh, you have something to share, I know it. You're just dying to share something. Okay, all right. Huh? You're just laughing at me? Okay. I was dressed a lot nicer this morning. I had my nice long-sleeved shirt on, my button-up, my khaki slacks. What we're teaching my 3-year-old, we're potty training my 3-year-old right now. So this morning as we were getting ready to leave, there was a wee accident. Thank you. I hope you picked up what I'm putting down there. Okay. Well, let's jump on in then. Alrighty. So we're talking about igneous rocks and intrusive activity. Igneous rocks, you've heard that term already. We learned that last week when we talked about the rock cycle. Anyone remember what igneous rocks are? What type of rock are they? Well, let me ask you this. What were the three types of rocks? First one's a gimme. It's right there on the screen. Igneous rock is the first one. What was the next one on our rock cycle? Say it louder. I can see it. Huh? Feldspar is a mineral. Yes, that's a mineral, which is present in all three types of rocks. But we're talking about the types of rocks right now. Brief overview of the rock cycle. We get our magma. Magma cools off into igneous rock. Igneous rock is exposed at the surface. It weathers, breaks down, it becomes sediment. That sediment gets turned into? What's the one that comes before that? Sedimentary, right? Sediment becomes sedimentary rock. Okay? Then it gets buried, it gets heated, it gets pressurized. What's the next thing? That heating and pressurizing is a process called metamorphism, which makes metamorphic rock. You see how the process kind of leads into that rock type right there? And then that gets heated and pressurized even more until it melts and we get back to magma and we start the rock cycle over again. Okay? So we're talking about igneous rocks today. Describe to me what you're seeing in these videos. I'm going to stand over here since most of you are over there. What are we seeing here? What do we got? Say it out, loud and proud. What do you see? Don't be... We're going to have to relearn this week, I guess, right? There are no dumb answers. Please don't be shy around me. Just yell it out. What do you see? Lava, thank you. Anything else? You see anything else? Leroy, what do you see? Rock. Okay, there's definitely rock around the lava. Good observation. It's molten. It's melted. Okay. We're looking at melted rock, and yeah, there is solid rock around it. There were gases coming out of it, right? It was bubbling, spouting out. There's so many observations we can make about these videos. Okay, so what we're looking at here is magma. Well, technically, like I mentioned last week, magma is what we call melted rock under the surface, and lava is what we call it at the surface, okay, at or near the surface. Magmas and lavas have three different phases to them, the three different phases of matter, right? Solid, liquids, and gases. All three are present in magmas and lavas. Hold on a second. Didn't I just say that magma and lava are melted rock? So why am I now saying that it has some solid and gassy stuff in it too? Any ideas? No? Well, that's fine. I'll give you the answer in a little bit, but I want you to remember the question, okay? Why would magmas have solid and gassy components as well? Okay, we will get there. How does magma get to the surface, though? Okay, because remember, we already talked about what's under the crust. Is under the crust liquid? No, under the crust is the mantle, and the mantle is in what state? Is the mantle solid, liquid, or gas? Solid. The mantle is all solid. The deeper you get, the squishier it gets because it really wants to be melted, but it's under too much pressure, right? That's what we learned about the mantle. Okay, but it is solid. So how do we get liquid rock at the surface? Aha, we shall answer that as well. But what's happening in the meantime is the hot, solid rock in the mantle is rising up from deeper in the mantle. because of this process we learned about called convection. Remember convection? Convection is the rise of hot material because it becomes less dense than the cooler material around it. So as less dense stuff is rising because of the heat, more dense stuff is falling because it loses temperature, just like a lava lamp. This is heating up the stuff on the surface down here, or on the bottom down here, which as it becomes hotter, becomes less dense, makes a bubble that comes upward, rises through the less or the more dense material around it, comes up to the top, cools off, and then falls back down to the heating element. That is convection in a nutshell. And this is what's happening in the mantle to bring hot mantle, still solid mantle, but hot mantle up near the surface, under the crust. We'll come back to this idea in just a little bit. What happens when we are heating something up? What are we adding? Heat is a form of what? Well, heat is an expression of temperature, but as you are adding heat, aka increasing temperature, what are you doing to your material? You're giving it more what? Not pressure. Heat is a form of energy. Okay? Remember how I said my answers are usually more basic than you think they are? Okay? Energy. As you are adding energy to atoms, they are vibrating faster. And so if I have atoms that are holding a bond, and I'm adding energy to it, aka making those atoms vibrate faster and shake faster and faster and faster, is it easier or harder to maintain those bonds? Harder. Definitely harder. And so as I add more energy, aka increase temperature, make it hotter, and my atoms are vibrating faster, they are not going to be able to hold those bonds, and they are going to disassociate. They're going to fall apart from each other. And this is the process called melting. When you take that chocolate bar and you heat it up, you are adding energy, which is you're breaking bonds. This happens to pretty much every substance, including rock. So as we are adding heat to our rocks, bonds start to break apart. We go from a solid crystalline framework to a loose conglomeration of random atoms, some of which are still holding bonds, but most of which are broken apart from each other, and make a liquid. Now what happens if I heat that up even more? I add even more energy. These atoms cannot stand being anywhere near each other. They have so much energy that they just zing and bounce off each other when they come close to each other. What do we call that? That's a gas. Think steam, right? Ice, solid crystalline framework. We already established ice as a mineral, right? I blew your minds last week. Then you add some heat, becomes a liquid. Still a unit, still somewhat cohesive, right? It's all together, it's just not in a solid framework. But you add even more heat to that, it becomes steam. What does steam do? Rises, dissipates, right? Goes away. So much energy is present that they cannot collect with each other. Now let's look at this process in reverse. We take that steam and we remove heat from it. What are we doing? What's water going to do, I should say? Yeah, it's going to go back to being a liquid. As it loses that energy, it's willing to come closer and hang out with each other again. Then as we remove even more heat from the equation, what are my atoms likely to do? Yeah, they're going to make those bonds with each other again because the bonds are now a stable condition to be in. Okay? Hooray, we have the whole gang. Okay, so this is our process. Add heat, solid, liquid, gas. Remove heat, gas, liquid, solid. Okay? I gotta sneeze, hold on. It's like right there. It'll catch me by surprise later. All right. Okay. Now as this is happening to rock, our magma is going from a liquid state to a solid state and becoming igneous rock. When we are heating any kind of rock, igneous, sedimentary, or metamorphic, it goes from the solid state of whatever type of rock it was to magma. regardless of whatever the rock was originally. Whichever of the three categories it fit in, all rock melts back into magma, which will then form igneous rock when it cools off. All right, so let's talk about how we classify igneous rocks. The first way that we classify them apart from each other is by describing the environment that igneous rocks form in. There are two types: intrusive. Bless you. I see my sneeze left me and found you. Okay. Intrusive, which means that they form in the ground. Pretty easy to remember that. Intrusive, in the ground. And extrusive. What do you suppose that means? Yeah, on the surface, right? Above the ground, outside of the subsurface. Okay? So intrusive, in the ground, extrusive, on the surface. Now, this is not in any way a description of composition or any other characteristic other than where it cools off, where the rock forms. Okay? So some examples of intrusive igneous rock: granite. Some examples of an example of extrusive igneous rock: basalt. How can I tell an intrusive from an extrusive rock? How can I tell just by looking at it, oh yeah, this formed underground, or oh, this formed on or near the surface? How can I get that? I look at the rock itself. Here I have granite, and here I have basalt. Right off the bat, just looking at these, camera doing its thing again. Look at me. Look at me. Thank you. Just looking at these, what can you tell me about these? Describe how they look different.
The one in your left hand is much darker.
Okay, color, definitely. What else?
The shape, lighter.
Shape? Of what? Oh, of the rock? Well, this is a piece of countertop that I broke and I cut and broke, and this is a naturally occurring. So let's ignore the shape of this and just tell me some other observations that you see about it.
One is a bunch of different colors.
Lots of different colors, which are associated with what? We see different minerals, and you can see them. Here's a big observation. Can you see the minerals in this one? No. Can you clearly see the minerals in this one? It's probably the first thing that jumps out at you. Obvious crystals in this one, none that you can pick out in this one. And this is the easiest way to tell intrusive versus extrusive. Why would crystal size make a difference for cooling underground versus cooling above the ground? What's happening to my energy as my magma is cooling off? I'm losing energy, right? Do you suppose that's going to happen faster or slower at the surface versus underground? Why would it happen slower on the surface?
Because there's not as much pressure.
What does pressure have to do with it? Pressure doesn't make rocks. Pressure makes sedimentary rocks. We're talking about igneous rocks. No worries. Would it cool off faster or slower on the surface? Why faster? Think about all the things it's exposed to. Yes, atmosphere, water. How much rock gets pushed out of the crust underwater? Most of it. Most of our surface is covered in water. Therefore, most of the igneous rock that's generated at the surface is underwater, right? It interacts with other rocks which have already cooled off at the surface. There are so many things up here that suck the energy out of that lava now that it's up here. So it cools off way faster than the magma that is still underground. Okay? So now go back to what we discussed last week when we learned about matter and minerals. Silicon tetrahedrons are forming in my magma. Metals attached to those. I have the first seeds of my silicate minerals, which then grow upon each other and make my mineral crystals. The more time that my minerals have to grow, the larger they become. The less time they have, the smaller they stay. So the rock that has the big crystals must have cooled off where? Underground. Making it which one of these? Intrusive. There you go. That's the easiest way, the fastest way to tell intrusive versus extrusive crystal size. Crystal size is big, lots of time to cool off, energy lost slowly, must have happened underground. Crystal size small, less time, energy lost quickly, crystals stayed small. Easy to remember? Great. Okay. So that's intrusive versus extrusive. Again, just a description of a cooling environment. That's it. Nothing about composition or any of that. All right? Now, let's talk about composition. So we learned about cooling environment. We're moving on to what are the rocks made out of? Okay? Composition. The first composition is felsic. And for this, I'm going to bring back our friend. This is granite. Okay? In case any of you didn't know that already. Granite is an intrusive, felsic, igneous rock. Felsic, a description of composition. I'm going to break that word apart. Think fel and sic. Where fel, think feldspar, and feldspar is what? A light silicate, one of the most common ones on our planet. Okay? And silica, meaning it is high in silica. Well, why does that matter? I'll come back to that in a second. Feldspar, silica, think of those two words together, felsic. So it is describing, this word describes an igneous rock that is high in light silicate minerals, as you can tell by the color. Felsic rocks tend to have less than 10% dark silicate content. This one looks like it has more than that, right? There's some blacks in there and some dark grays. Well, those dark grays, I'll pass this around in a second. I'm going to show it to the camera first. If you look closely, those dark grays are actually just clear. Those are clear quartzes. It's just that they are appearing dark gray compared to the other rocks around them. Okay? And quartz is a light silicate, not a dark silicate. So when you really look at it, you'll notice the amount of actual black minerals in this is approximately below 10% of the total volume. Granite is a classic example of a felsic igneous rock. Now I mentioned silica. What does silica have to do with anything? Remember that silica is required for those silicon tetrahedrons to form, right? You can't have a silicate mineral without silica to make the silicon tetrahedrons. There is an inverse relationship between the amount of silica available in my magma and the dark silicates in that magma. The more free silica I have, the more light silicates I'm going to form. And therefore, the lower my iron and magnesium-based minerals are going to be. The more iron or magnesium I have, the less silica there is to make those light silicates, like quartz. So, inverse relationship here. So when I say felsic, think feldspar and silica, I'm telling you think high in free silicas, making extra light silicates. Okay? Then we have mafic. Mafic is on that inverse spectrum there, where we just looked at a high silica, high light silicate rock. Now we're looking at a high iron and magnesium, low free silicate rock. Okay? Basalt is an example of a mafic igneous rock. Now earlier, Lexi, I think, pointed out the color difference between these two as an identifier. That's great. The color in this is generally darker. Do you think it has more light or dark silicates in it? Dark. Excellent deduction. Yes, it's made out of mostly dark silicates. Great. That is what mafic means. Let's break down that word. Mafic. May, think magnesium. Fic is the suffix for iron in pretty much every word that includes it. Okay? Mafic, iron and magnesium rich, aka low in free silicas. We call that a mafic igneous rock. That's its composition. Basalt is the type of igneous rock that makes up most of the ocean crust. for reasons you're going to learn about later today. Now, intermediate. What do you suppose intermediate means? Not necessarily both. In between, right? It's what we call it when you have a composition somewhere between mafic and felsic. Okay? And you get something like that. And immediately you're thinking, oh, okay, yeah, that makes sense. It's like half light silicate, half dark silicate. That makes perfect sense for why we would call this intermediate. Well, you're right. This is called diorite. This is an intermediate composition igneous rock. Would you describe this as intrusive or extrusive? Intrusive? Why? Bingo! There it is. You can see the crystals. Though if they're large enough to see, you're looking at something that formed relatively slowly underground. Perfect. Then we've got, there it is, thank you. Thank you. Then we've got ultramafic. When I say ultramafic, I want you to think mafic but more. It's not just mafic, it's ultramafic. Okay? So this is like your deep mantle stuff. There is nothing but iron and magnesium dark silicates in that. Okay? So just olivines and pyroxenes in this example. This is that peridotite mantle rock, that deep mantle rock I passed around last time. That is ultramafic in composition. Okay? I'll show it to the camera again. I won't pass this one around. All right. So those are your compositions. So we've got your that inverse relationship, which I already told you about. If your mineral, or if your rock, excuse me, is rich in silica, it's going to be low in iron and magnesium. If it is rich in iron and magnesium, it's going to be low in silica. Not only does this affect the composition, it also affects the behavior of your lavas and magmas. If the amount of silica present dictates how many silicon tetrahedrons are forming early on into the cooling of this material, how might that affect the characteristics? Well, it affects something called viscosity. I'm going to go get something to demonstrate this with, but can someone tell me what viscosity is? What is viscosity? I got a shrug, which is better than nothing. Great, thank you for saying that. Does anyone else know what viscosity means? Thank you. At least you can read it off the slide, or hey, I gave it to you right there. What does that mean, though? What does resistance to flow mean? What is flow? If I were to say something flows, what's your immediate knee-jerk reaction to that? What does it mean?
Water.
Okay, water flows, but what is flow?
The direction.
Is it the direction or the fact that it's moving? Flow is movement. Direction is where it's going, right? Flow doesn't describe direction. It describes that it's moving at all. Okay? Yes, resistance to flow, though, viscosity is a measure of how difficult it is for that thing to move in the environment it's in. Water, thank you for that example. Fairly high or low viscosity, would you say? Is it very resistant to flow or easy to flow? Easy? So you would say it has low resistance to flow. So we would say that this is a very low viscous liquid, and you would be right. Water is kind of our baseline measurement. There are some things that flow easier and a lot of things that flow harder, right? Not as easy to flow. For example,
Honey.
corn syrup, but close. Oh, is it even moving? Yes, it is. It just happens to be 28 degrees outside, so it's going to take a while. This is corn syrup. And when we give it a little bit, that corn syrup is going to flow. But is it going to flow faster or slower? It's going to flow real slow. Would we say that it is highly viscous or low viscous? High. It's even worse than it was when I taught your class. All right? Okay. The amount of silica present in my magma dictates how many silicon tetrahedrons can form, which will in turn dictate the viscosity of my liquid. How does it do that? Well, what's the difference between these two things? One is clearly thicker, right? However bound up my liquid is going to dictate how easy it is for it to flow. So if I have more silicon tetrahedrons forming, binding up the atoms in my liquid, then it's going to make that liquid more difficult to flow. It's starting to move. It's getting there. It'll bloop down in a minute or two. Okay? So more silica, aka more felsic, magmas have more viscosity. This is a mafic flow. Low in free silica, high in iron and magnesium. It's pretty standard flow for that. This is a felsic flow, crawling along. You can actually see, you see those kind of spiderweb networks around that is the beginnings of forming minerals on the surface of this flow. They are forming as it is moving.
So the richer it is in something,
There it goes.
the slower the flow?
The richer it is in silica. More silica is the key. The higher the silica amount, look, here we go, right there. The more silica it has, the slower the flow is. Oh, it's so. Can you believe we eat this stuff? Do you know how many things have corn syrup in them?
It's America, almost everything.
Just about everything. Yeah, has this stuff in it. Which, by the way, your body can't process, which is why we are growing
Have you ever actually
more.
cooked with it?
Oh, yeah.
It's so annoying.
It's very annoying. Oh, look at this. It's going to gloop. See if I can actually get it down through the neck without letting it touch. Oh. Oh, I failed already. It touched on the side I wasn't watching. All right. But you get the idea, right? Very highly viscous. Most candy's made out of that. So are most sodas, sports drinks, energy drinks, etc. Okay. Where was I? Oh, yes, the viscosity. All right, so more silica, more viscous. Okay. So I'm going to play this video. Listen, tell me what you hear from this video. You're going to hear some wind. Try and listen past the sound of the wind and tell me what it sounds like. What does that sound like to you?
Glass breaking.
Can we agree it sounds like breaking glass? You're absolutely right. That's exactly what it sounds like. It's way louder in person, by the way. Like you walked into a China store and you're shattering everything in sight. Okay? Why does it sound like breaking glass as this lava flow is moving?
Because the top layer is already cooled.
The top layer is cooling. And then what's happening?
The hot magma is pushing through it.
The lava's pushing it, breaking the material that forms on top. But why does it sound like breaking glass? Because that's what it's making. When you cool off magma or lava very quickly, like in this situation here where the wind is cooling off the top surface very quickly, you don't really have enough time for more than your silicon tetrahedrons to form before it cools off and crystallizes and nothing can be mobile and nothing can form a new bond. This makes something we call volcanic glass, otherwise known as obsidian. This is how we make obsidian. You cool off lava real quick. Introduce it to extremely cold temperatures or douse it with water. Don't give it time to cool off slowly. You get obsidian, volcanic glass.
A lot of like arrowheads are made out of.
Yeah, a lot of arrowheads, especially in this part of the country. The American Southwest, where we have a lot of obsidian sitting around because this area has been very volcanically active for a long time. Lots of obsidian sitting around. The Native American tribes would pick it up. They learned how to chip it into arrowheads, spear points, things like that, tools, knives. Up north, where you have a lot less obsidian, like the tribes in Michigan and Ohio and stuff, we actually have found like tons and tons of ancient villages out there that have tools and weapons made from obsidian from down here because the tribes would trade with each other because the tribes down here had that resource and the tribes up there didn't have that resource, and so they would trade with each other for it, right? Fascinating history. You see in front of the mic? There we go. Thank you. Okay, great. So you all caught on quick. That's glass. That's what that sounds like. That's why it sounds like glass, because it is glass. All right, next up we're going to talk about igneous textures. So you've learned about, oh, his head's over here, isn't it? His head's over here? Yeah, I felt something touch my tongue and I was about to swipe it like it was a bug, but then I realized it was probably his tongue. What was I saying? Oh, igneous texture. So we learned about cooling environment as a characteristic. We learned about composition as a characteristic. Texture is the next thing. Texture is a description of the size, shape, and arrangement of the minerals in my rock. This is dictated not only by the cooling rate, but also whatever minerals formed, how much silica there is, how many gases were present. There's a lot of characteristics that go into the texture of my rock. It's kind of the same process of elimination I'm teaching you that you learned from minerals, the minerals lab, okay? Where you collect all these traits and then you use the traits to process of elimination, figure out what it is on the Excel spreadsheet. You're going to do the same thing with these igneous traits for these rocks. But good news, there's way less of them, okay? Way less properties and only 12 samples for this lab versus the 24 for lab 1, okay? Okay, so the only exception to the rules of texture is volcanic glass. It cooled so quickly, we call that quenching, by the way, when you cool something instantaneously. No crystals formed other than silicon tetrahedrons. It's literally just glass with a whole bunch of other loose ions trapped between it, giving it that color. So there's green obsidian, there's black obsidian, red obsidian, white obsidian, rainbow obsidian. There's all sorts of different types of obsidian. I'll show you some of them later. But they have those unique colors because even though they are just straight up glass, a whole bunch of other stuff that was in the lava got trapped in between the glass. Okay? All right. Any questions so far before I jump into the first of the textures here? Are we following along? Are we confused about anything? Okay. First texture, aphanitic. Aphanitic texture, let me move these out of the way so that the camera's not looking at those instead of the screen. Aphanitic texture are those which have crystals so small you cannot see them with the naked eye. Not only is that a great indicator that it is extrusive, it's also a description of texture. You can get this 2 answers from making the same observation here, okay? So aphanitic describes the crystal size here. Cooled quickly near the surface. It's a pretty good observation there to make, or a pretty good hypothesis to make from that observation. Now, another texture that you may find associated with aphanitic rocks is called vesicular. You see how this rock is full of holes here? What do you suppose made all of those holes? Bugs? There are not very many bugs that will eat or burrow into rock. So, no, but interesting. It could be a really dumb bug. That's true.
I'm guessing other already cooled crystals.
Okay, so you're saying already cooled crystals that are not there anymore?
That it was like growing into, but it didn't stick to, if that makes sense.
This is a very good thought. It's not the answer, but following that line of thought, I want you to come back to that in a couple of slides here, okay? What else could have made these holes? Do you suppose these holes were made after it turned into rock or before? Why would it need to be before?
Bubbles.
Well, sure. Yes, they're bubbles. Bubbles don't form in rock. They form in liquid. So those bubbles would need to be there before it became solid, right?
Like bread.
Yeah, like bread. Well, except with bread. Oh, okay. No, I kind of like this. I like this. Let's dive into this. Why do you get those bubbles in bread? What's happening?
It's trapped air.
It's not actually.
Okay, we know about baking soda.
No, it's okay. No, it's okay. What's making those bubbles in your bread is the yeast. What is yeast?
It's a protein in the flour that allows it to get larger and rise.
It's not a protein. It's bacteria.
That one.
Yeah, yeast is bacteria. It is a living thing that when you put it in your bread dough, begins consuming the sugars in your bread dough. As it consumes the sugars, it is releasing gases. Those gases are trapped in your bread dough, making the bubbles, which get trapped there and stay there once you cook your bread and take it from that kind of semi-solid state to a fully solid state. The gas bubbles remain. That is what makes the holes in bread. And that's actually a very good comparison to what happens here. There's no bacteria causing this, though. What's causing the formation of these gas bubbles? The fact that we are losing temperature at all. When you go from one state to another, liquid to solid, solid to liquid, liquid to gas, whatever the case may be, changing that state of matter often has the byproduct of not needing all the same stuff you had before. So you'll let off hydrogen, you'll let off oxygen, you'll let off carbon dioxide, sulfur dioxide, nitrogen. You'll let off a lot of gases that you no longer need in your new state. So if I'm going from a liquid to a solid, I'm going to release gases. Okay? And those gases are going to get trapped because my fluid is too dang viscous to let it out. That is where we get vesicular texture. Okay? So here's a cool picture. Take a look at this. This is a picture from a sideways view, a cross section, if you will, of a lava flow, basalt, as it would happen to be. How many vesicles do we have down here near the middle of the flow versus near the top? There's a lot up here and very few down here. Why?
I'm guessing that all the bubbles rose to the top, and the top was cooling off faster, which was making the flow slower and making it more resistant to the bubbles.
Okay, Ilani, what are you thinking? That's what you were trying to say? Great. Do you want to add anything to it? Okay. You are both correct. Okay? Hotter down here, therefore less viscous. Bubbles were able to form there, but where do they want to go? All bubbles are trying to go where? Why up? When you're saying compacted, what's another word you could use?
I don't know, you've been saying it all day.
When you compact something, you are increasing the pressure. I have more pressure down here. My bubbles are under pressure. And where are they trying to go? But why up? Out to why? What is drawing them there? Why are they compelled to go there? Yes, but why? Huh? Oxygen is part of the component here. It's one of the gases. Why are they compelled to go up in this case? Why do bubbles in water rise? Where do they rise? the surface because what? Yes?
Because heat rises?
It doesn't have, okay, it's not the same thing. I see why you were thinking that, but it's not the same thing. If my bubbles are under a lot of pressure down here, why are they trying to leave it and where are they trying to get to? Less pressure. That is where all bubbles try to go, regardless of where they are or what they're doing. They're trying to get to zones of less pressure. So what has less pressure than this lava flow? The atmosphere. So our bubbles form down here at the middle, are able to leave the middle because it is still relatively non-viscous. But once they get up here where it's cooling off faster and becoming more viscous, they get trapped and there we get more vesicular texture. Does that kind of logic track? Are we following that logic there? If not, I can go over it again. Boo. You're just mad you were not correct. Yeah, I get it. But keep them coming because you will be correct a lot of the time, I guarantee you. Okay. Next texture, phaneritic. Phaneritic textures have the large crystals easily seen by the naked eye, which means they cooled slowly down below the surface. Okay? That one's pretty self-explanatory, right? All right, next up, porphyritic. Porphyritic means that you have microscopic crystals and large, easily seen crystals. It's like a combination of the other two. In what circumstance would I get that? And this is coming back to the idea that you had earlier. You were talking about a separation between large crystals and small crystals. It wasn't quite right for this, but it's in the right ballpark. Why would I have a rock that has small crystals and large crystals if we learned that large crystals form over long periods of time and small crystals form over short periods of time?
Because they grow into them and then break off and get stuck in them.
Oh, okay. Fun idea, but not quite correct. No. You guys are all dancing around. You're both dancing around the idea. Yes?
New theory. So the smaller crystals cooled off faster, and then the larger crystals, since they were still cooling off, they kind of formed around them.
Except they're not around them. They're in them. They're in between them.
They merged.
Reverse that idea. So reverse it. What then would happen? I didn't cool off crystals quickly and then other ones cool off slowly. That wouldn't work. I'm cooling off the rock at the same rate. So then what must happen? Take that idea and flip it. Alani, do you know what I'm going for here?
I can hear her. I was hearing you and her, but I didn't really hear what she said.
Here I have a porphyritic igneous rock made out of large, easily visible light silicates, which you can see, and microscopic darker silicates, which you can't see, but you know are there because the coloration is there between the light crystals, right? If I have a magma that is capable of making multiple types of minerals, which they all are, but one mineral forms at a certain temperature before the rest, which we know from last week they do. Minerals have melting points and therefore crystallization points. If I take my magma and I start cooling it off slowly, then I'm going to start forming some minerals that have a lower melting point, or excuse me, a higher melting point while we're still at high temperatures, and therefore a higher crystallization point. I take a little time, maybe a couple hundred years, I start forming these larger crystals, but before the entire body of magma can cool off underground, it all gets shoved up to the surface where the rest of it cools quick. So I have large crystals that had time to cool slowly surrounded by the rest of the magma, which was forced to cool quickly, which made the microscopic ones. You following me? Now, there's one other way that this can happen, which is more along the lines of what you two were talking about here. What if the opposite thing happened? What if I have a rock with large crystals, like a granite, that I start to melt, and mostly melt, but not all of the crystals melt. I don't quite reach the melting point for all of the crystals. Then I take that partially melted magma and cool it off quickly. I get the remaining original crystals from the original rock surrounded by the newly formed microscopic crystals, which is kind of the idea that you two danced around earlier, right? So those are the two ways you can get porphyritic igneous textures. Yeah, I'll move them at the end of the class. Luckily, there's no one sitting across from you, so you can also stick them over there. Okay. We've got our friend obsidian. There's lots of different types of obsidian. Rainbow, snowflake, mahogany, what I passed around earlier, what I showed y'all earlier. Did I pass it around? Yeah, I did. It's called mahogany obsidian. It's got some red and some black in it. What gives it the coloration? Whatever's trapped in there in the glass. Okay. You can actually take igneous rock, melt it, and then instantly quench it and make obsidian. I've done it in a lab before when I was working on my bachelor's degree. We went into the lab. We get a crucible, a porcelain crucible. We powder up some basalt rock, pour it in there, and then we use like a propane torch, and we melt that sucker. Okay, we just melt that powdered basalt until I have just a little bead of lava at the bottom of my cup. And then I turn this off and douse it in water. Instantly turned into this beautiful, bright green ball of glass. I still have it somewhere in my boxes in my office. I've worked here for, I'm into my 6th year now. I haven't fully unpacked my own rock collection. Some of the pieces are scattered around this room. A bunch of them are in the display cases out there. I still have like 10 boxes of rocks that I haven't unpacked. And probably never will if I'm honest, but it's in there somewhere. Another really cool way that we can see volcanic glass form is this. In Hawaii, where you don't have particularly violent eruptions of lava, which we will talk about later, instead you get it spits lava out of the volcano constantly. And so as it's spitting out lava, as these lava chunks fly through the atmosphere, they kind of string themselves out through the atmosphere and cool off quickly before falling in the water and cooling off extremely quickly. And so you get these very thin strands of volcanic glass that wash up on the beach. They call this Pele's hair. It's a very cool way of obsidian forming. It's like you pick it up and it crunches like glass. It's like you be very careful when you do that. You don't want to get glass splinters or anything. It's crunchy like glass, but it has the thickness of human hair. Pele is the Hawaiian goddess of fire and creation, goddess of volcanoes. So that's why we call it Pele's hair. All right, the next texture, pyroclastic. Now I told you something last time when we talked about the rock cycle. I said that igneous rocks can only be made from lavas and magmas, right? There's one exception. You can also get a type of igneous rock from a volcanic eruption, not from the cooling and crystallization of lavas and magmas necessarily, but as the product of a volcanic eruption. What is a volcanic eruption? It's a big boom, right? As part of that big boom, it shatters and partially melts the rock on that volcano. And any rock that's made as a result of that, from the ash and the debris from the volcanic eruption, is also classified as an igneous rock. It has to do with the igneous process, therefore we group it with igneous rocks. That is pyroclastic. Pyroclastic texture means it's not made from crystals, it's made from the shattered fragments of a volcanic eruption. This is volcanic breccia, we call it. You can tell by seeing that it's basically like all the pieces are broken, jagged, fractured, destroyed chunks combined by microscopic ash, basically, volcanic ash that's combining them all together. So that is a pyroclastic igneous rock. The last texture is called pegmatitic. Pegmatites are types of bodies of igneous rock with crystals larger than about 2 centimeters. When most of your crystals are larger than 2 centimeters, we would call that a pegmatite. Like that. That is one quartz crystal, one feldspar, one feldspar, one feldspar. Look at all of those big micas in there, okay? This is a piece of a pegmatite. Now, pegmatites are really cool because the biggest minerals form in those. Pegmatites form at the very end of the life cycle of a magma chamber. I'll explain that in a little bit. But pegmatites are very valuable because that's where we get most of the rarest elements on Earth. Anything basically that's left over that has not formed into a mineral so far during the life cycle of a magma chamber is forced to form into a mineral or combine with something when pegmatites are forming at the end of that magma chamber's life. And they make very large crystals. This right here is one crystal of feldspar. The largest known crystal of feldspar was the size of a 2-story house. Clearly, I can't have that in my collection. Okay. This is a picture of the Nica mine in Mexico. Used to be open to the public. My great uncle actually has a picture. He was a geologist. He actually has a picture of himself in here. For scale, that is a person standing right there. Okay. My great uncle has a picture of himself standing on this crystal right there in that V shape. That was back in the 70s. Can't do that anymore. Matter of fact, this is completely closed off to the public. But because there are so many rare elements there, they use them for mining a lot. Okay. Any questions about igneous textures? Okay. So how do you go about identifying igneous rocks? You use all of these characteristics that we've talked about today. So you're going to know, is it intrusive or extrusive? You're going to try and find the composition. You're going to identify the texture. You're going to use all of these things and essentially through that process of elimination, figure it out. You can, make a sort of basic framework out of this, where anything that is intermediate and phaneritic is most likely a diorite. Anything that is mafic and aphanitic is likely a basalt. Things like that. Okay? But before you can make something like this, you have to know more of the different types of igneous rocks you might see. So that's what we're going to go over next. We're going to go over the basic types of igneous rocks, the ones that are most common, what classifications they fit into, what their properties are. And that's what we're doing next. All right, so first off, granite. I'll hold up the granite again, even though you've seen it a bunch. Granite. Intrusive, felsic, phaneritic, igneous rock. We all understand those words now? When I'm looking at this and I say phaneritic, you all know what I'm saying, right? When I'm looking at this and I say felsic, you all know that I mean mostly like silicates, right? That's composition. If I said intrusive, felsic, phaneritic, igneous rock, everyone's minds should probably jump straight to granite because that's the most common of that particular type. Okay? Now, something about granite is if you ever go to buy a house or make a countertop or anything, you go to a countertop salesman, you tell them you want granite, they're going to offer you 20 different types of rock. And they aren't all going to be granite. Okay? Granite has distinct characteristics. Having made several countertops and having to go and buy the rock myself, I'll tell you, most of what they will try to sell you is not granite. One of the benefits of taking my class is you will never get ripped off by a countertop salesman. Hey, real life application. You don't even have to be a geologist, right? You know that a granite has to be mostly like silicates. It must include some proportion of quartz. Okay, things like that. Do you want me to pass this around again, or are we good? It's like, no, less rocks, please, please. Yeah, I have the whole other half of that table to fill in. Okay, now the extrusive version of granite, because remember, granite has those distinct characteristics, but if I take the same magma that made granite and instead push it to the surface so it cools off quickly and becomes extrusive, we get rhyolite. Rhyolite has mostly microscopic and therefore microscopic crystals and therefore has an aphanitic texture, but it is also felsic just like granite. Rhyolite is pretty rare to find on the surface in flow form. We find it all over the place, but it's rare to find in consistent flow form. Why do you suppose that is? Rhyolite is felsic in composition, I will remind you. So why would that make a difference for how rare it is to find it flowing on the surface? How quickly does felsic lava flow? Remember, felsic means high in silica. Silica means high resistance to flow, doesn't move fast. So if I have a lava flow on the surface that is felsic in composition, is it going to go very far? No, it's not. So we don't typically find them a whole lot. Okay, obsidian. Wait a second, why do I have obsidian in the felsic category? Isn't it black? It's dark colored. So why don't I have it with the dark silicate-based minerals, the iron and magnesium-rich ones? Is it practically clear? I mean, yeah, sure, you shine some light through it. Yeah, definitely around the edges, it's clear. And that's basically what it comes down to. It's not, that the characteristic isn't around the edges, it's clear. It's made out of glass. Glass, pretty much just silica. Just silica, making it felsic in composition. The stuff trapped between all the silica, that doesn't classify, that doesn't characterize it for what it is. For the same reason why quartz has so many different colors, but it's all types of quartz, and all quartz is a light silicate. Obsidian is felsic, even though it has dark coloration, because its actual atomic framework is just the silica. Okay? Pumice. Have you ever heard of pumice before? Pumice stone. You ever been to a spa? They use pumice to exfoliate you, scrub the bunions off your toes, things like that. Do you know that pumice is a rock? You know that pumice is an igneous rock? Yeah, pumice is actually really cool. Pumice is essentially obsidian. But what's different?
I'm guessing it was cooled down very slowly.
Why?
There is holes in it.
There are holes in it. What does that have to do with cooling down slowly?
It means the bubbles were being released slower because they were trapped.
It's actually the opposite.
What?
The bubbles didn't have time to leave because it cooled so quick.
That one. Yep.
Does that make sense?
What I said reversed.
Okay, yes, exactly. What you said reversed. Okay, so what we have here is essentially lava that was filled with gases and then cooled so quickly that the gases didn't have time to escape, and so we're trapped in bubbles. There are so many bubbles in pumice that this is the only type of rock in the world that will float on water. So much of the volume of this rock is bubbles, is holes, that it will actually float on water. Its density is less than that of water. I'm going to pass this around. Please don't scrub your fingers with it. She's purposefully going to do it now. Okay. Okay. Let's move on to intermediate. The extrusive, intermediate, aphanitic igneous rock you're going to learn about is called andesite. Andesite. From a distance, it looks pretty grayish. Most andesite typically is. When you look up close, you can see that there are a few distinct white and black things that you can see, but for the most part, it's pretty gray. A relatively even mix of light and dark silicates. Okay, I say relatively. There's a gradient here. It can be anywhere from 25 to 50 to 60%, one or the other. But all of that fits in the category of intermediate. Okay, somewhere proportionally equal is what we're looking at here. Called andesite because it was first characterized in the mountain range running along the west coast of South America, which we call the Andes. Therefore, andesite, because most of the rocks over there are some classification of this. Okay, so there it is. Pass that one around too. We've already seen the phaneritic version of that, diorite. I already got past that around. It's sitting in front of Lexi. Okay, the diorite. Some people call it zebra rock. It's not particularly, accurate because it's not in the stripes. Salt and pepper rock, some people call that, but its actual name is diorite. Diorite is one of the other rocks that is commonly confused with granite. They will often try to sell you diorite as granite. But you know the difference. Diorite is intermediate and does not typically contain quartz. It would, but what's the problem? We learned about mineral traits. Why is the presence of quartz so important for something like a countertop? Are you heating your countertop to 400 degrees Celsius? If you're putting something 400 degrees Celsius on your countertop, you are on fire. Yeah, it's more difficult to break. What's the hardness of quartz? Mohs scale of hardness, 1 through 10, remember? Quartz sat at where?
9.
No, but good guess. 7. Corundum is at 9. Corundum just sitting there right under diamond, which is at 10. Corundum, another word for that. So corundum is a scientific name. You know those as rubies and sapphires. They're the same mineral, corundum, just different colors. But no, quartz is a 7, making it harder than most other substances that your countertop will come in contact with. Okay? Unless you have a ruby knife, you ain't cutting through that. Right? It's highly unlikely. It's even harder than steel. Stainless steel has a hardness of 5.5. I didn't break anything. Okay? It's a hardness of 5.5. Whereas diorite, without quartz, mostly amphibole and feldspar, which have a hardness between 5.5 and 6.5. So there's a lot more things that have the potential to break and chip and scratch your countertop if it's made out of anything other than granite. Very possible. Okay. All right. That's diorite.
Also, I don't know where your mic is on your little square, but Bro's like sandwiching it.
It's right here. The microphone's poking out right there. So they should be able to hear everything I'm saying. Let me just boop, boop. Yep. I just deafened everyone by pumping it. I've got a little reader here that tells me what the sound pickup is.
He's been like sandwiching it for like 15 minutes.
That's okay. Maybe he's repeating everything I say. He's just translating it into snake. Okay. All right. Maybe YouTube has a snake to human translator, right? No? Okay, moving on to mafic igneous rocks. Basalt, which I have also passed around, right? Aphanitic, extrusive, mafic igneous rock. The most common one on the surface of our planet. Why? It's because of something I already mentioned earlier, the first time I introduced you to it. Well, extrusive means that it is on the surface, but why is it the most common one? I'll give you half the answer now and half the answer in a little bit, so we can tie the two ideas together. It is the most common igneous rock under the ocean. And most of our planet is covered in ocean, right?
So it's cooled underwater.
It cools off quickly underwater. Yes, it also cools off quickly at the surface, but underwater is where it most often pops out. Why underwater is where it most often is pumped out, I'll explain in just a little bit. Okay, I'll tie that idea together with this one. Okay, gabbro is the intrusive version of basalt. So if you take that mafic magma, and instead of pushing it to the surface where it cools quickly into basalt, you cool it slowly underground, you make gabbro, which looks like this, and is often marketed as like a darker type of granite. Let me actually show it to the camera real quick. Okay, large crystals, you can clearly see those crystals in there. You can see their cleavage planes reflecting right back at you. Lots of different types, a few light ones, mostly dark ones. Mafic composition, intrusive, phaneritic. There you go. And then we've got our pyroclastic ones. Pyroclastic is going to be a couple of different types. I already passed around that volcanic breccia, which are the fragments of shattered volcanic rock that have been compressed together with volcanic ash. Okay, so a combination of large and small pieces of rock together. Yep, that one. This is called welded tuff. This is what happens when you're generally a little further away from the eruption. There's less debris flying away. It's just where the ash is falling. Now think about this ash. Ash is incandescent, extremely hot, microscopic shards of glass. I'll talk more about that on Thursday when we talk about volcanoes specifically. But what happens is this extremely hot ash falls on the ground and fuses together. We call that welded tuff. And this is some welded tuff right here. So, pyroclastic textures are those which are made from ash or broken pieces of rocks from a volcanic eruption. No crystals, just pieces, results from a volcano. Okay? Questions about textures or different types of rock? I just hit the highlights here. Lonnie, do you want me to give you a second with the slide? No, you're good? Okay. Then let's talk about something I mentioned earlier. I asked you where the magma comes from, right? Any thoughts on that now? Underwater volcanoes do exist. Those are called seamounts, but they need lava to come out of them just like the ones on the surface do. So clearly it can't just be them. I'm not asking where does it come out. I'm asking why is there magma in the first place? Because we know that the mantle is solid, right? We have a solid crust. Whoop. We have a solid mantle, way thicker, but still solid. Whoop. Underneath of that. Then our liquid outer core. Then our solid inner core. If the only liquid layer in our entire planet is the outer core and that never comes to the surface, thank goodness it doesn't. That would be disaster if it did, right? How do we get magma up here? Let's learn about it. Okay. We know that it's solid. Solid crust, solid mantle. But we also know that we get magma, liquid state rock up here. This is because of something called the geothermal gradient. This is the Tautona mine in South Africa. It's a gold mine. They get gold and other types of minerals out of here. Mostly gold, though, is the focus. This is the deepest mine in the world. When this graphic was made by National Geographic in about 2015, it was 3.6 kilometers deep. Okay?
That's approaching 2.5 miles. Okay. Underground. It is so hot at the bottom of this mine that human workers, it's practically unlivable. If you are a human worker, you have to spend most of your day in a refrigerator. Like you work for an hour and then you refrigerate yourself for like 2 hours to cool yourself off. It's actually gotten to the point where it's unsafe for most people to go down there. It's one of the places in the world where they are experimenting the most with robotic workers, because robots can survive the temperatures and humans cannot. Okay, I'm talking like 130, 140 degrees down there. Okay, and no wind. No wind. And like all humidity. Okay, so why is it getting hotter the deeper you go underground?
You're getting closer to.
I want to hear what Lonnie's saying here. What? You're getting closer to the core where it's the hottest, right? Things are hotter at the center, less hot as you move outward, but that means the deeper you go, the hotter it gets, right? Okay. This is the geothermal gradient. The geothermal gradient is the rate at which heat increases the deeper you go underground. Might be a good thing to take note of. The geothermal gradient is the rate at which heat increases the deeper you go underground. Now, as it turns out, that is not linear. This is a graphic that shows you the geothermal gradient. It's this hockey stick shape right here. So here on this side, this scale, we have kilometers. Here on this side, we have pressure. Yes, I have two y-axes here. Why? Because pressure increases consistently as you go down deeper, right? So it's okay to have them on the same axis as long as they are consistent with their measurement to each other, okay? So depth over there, pressure over here. Temperature on my x-axis. Temperature increasing the further right I go. What does our geothermal gradient do? It increases, but then it reaches a point at which it barely increases at all as my depth and pressure increase. Why? That's just how it's working, okay? That's just how the science worked out. It's this hockey stick shape. Now, notice this purple line is the partial melting point for peridotite, which makes up the mantle. What do you notice about the geothermal gradient and that partial melting point? Do they ever touch? No, they come real close, but they never actually touch each other, which is why the mantle is always solid. What has to happen for this to change? We have to change the dynamic. We have to change some of the characteristics of what is going on here. There are three ways that we can change this situation to cause rock to melt. The first one, increase the temperature. If I'm increasing the temperature, which usually happens thanks to tectonic activity, if I'm increasing the temperature, what am I doing? My geothermal gradient is moving in what direction? That way. Temperature is increasing that way. So I'm taking this geothermal gradient line, and because I'm increasing the temperature at that point, let's say 100 kilometers of depth right there, and I increase the temperature maybe 75, 100 degrees Celsius, all of a sudden, whoop, I'm over here. I have passed the partial melting point. Therefore, I can have melted rock. So increasing temperature, that's the first way. What's another way? Decrease pressure. Oh, hold on. Before I get there, by the way, where is somewhere that can happen? Plate boundaries. Here's my continental plate. Here is my oceanic plate. One is subducting under the other. Guess what? Right there, there's a heck of a lot of friction. Friction generates what? Energy in the form of heat.
So it's the product of
Tectonics is the driving force for a lot of the things you're going to learn in this class. Okay? Tectonics is, I'm not going to say it's the magic everything answer, but it's the answer a lot of the time. Okay? So that is the way we can generate more heat, more temperature. Okay, what about decreasing the pressure? What does that do? Well, here we are again at 100 degrees depth, or 100 kilometers of depth. Let's erase that. We're not messing with temperature anymore. Okay, so what happens if I decrease the pressure? Instead of moving this geothermal gradient horizontally along the temperature plane, we are decreasing the pressure vertically. If I decrease it enough, what's happened? I have now passed the melting point. Yeah. How can I decrease the pressure? Well, now let's say we're at a divergent plate boundary. Okay? At this divergent plate boundary, with mantle underneath of it, let me draw this a little better to show you what I'm actually talking about here. The divergent plate boundary is thinnest. The plates are thinnest right there at the boundary between the two plates, which means that between the two plates is this zone of low pressure. The closer you get to the surface, the less the pressure becomes. Like those bubbles in the lava we were talking about earlier that wanted to get up to the atmosphere, so does the mantle rock. So it flows up into that low pressure zone, and as it enters the low pressure zone, what happens? It passes the melting point, and we get magma.
So basically volcanoes are low pressure.
Some of them are. You remember I taught you about the ocean ridges, like the mid-Atlantic one, the one that slices through Iceland? Covered in volcanoes along the bottom of the ocean. Why? Why is Iceland so volcanic? This. Low pressure zone, melted rock, you get volcanoes. Okay? So that's the second way. The third way, now you're going to have to follow me on this one. You're going to have to take my word for it because I'm not going to take the time to teach you the chemistry for why. We don't have time. Water. There are some physical properties of water that we take for granted. If I want to cool something off, I'll douse it in water. I want to put out a fire, I douse it in water. I'm feeling hot. I drink water. I bathe in water. I cover myself in water. We tend to associate water as just the thing that removes heat. That's a physical characteristic of water. There is a chemical characteristic of water, though. Water lowers the melting point of rock. That's a chemical characteristic. If I introduce water to a rock, if I infuse a rock with water, if all of the available space inside of my rock, the microscopic spaces in my rock are filled with water, that rock is going to melt faster than it otherwise would have as a chemical trait of what water does. So all I have to do in my third scenario is introduce water to rock that is hot enough to be melted, and it will melt. Where could this happen? Let's go back to this subduction plate area, okay? I don't have blue, so I'm going to use green for water, okay? My ocean plate is covered in what? Ocean. Water, yeah. Which means that the top, at least several layers, probably half a kilometer or so, of my ocean rock is going to be saturated with water. And as it is getting shoved, subducting underneath of my continental plate, what's going to happen to that water? It's going to heat up. And what does water do when it heats up? Turns into a gas. And where does it want to go? Up. Okay. As it is going up, it's going to interact with the already super hot mantle rock just under the crust. And as it gets introduced to that super hot rock, it lowers the melting point. Now, what happens if my melting point lowers? At what direction am I moving my melting point? I'm not moving my geothermal gradient now. I'm moving my melting point. It's going that way. So now my melting point, which was right here, is now over here past my geothermal gradient. That is the third way we get magma. And so we get plumes of magma rising up from the water that was introduced to it by this subducting oceanic plate. Those plumes of magma chew their way up through the crust. And this, my friends, is what gives us all those coastal mountain ranges. The Andes, the Cascades, the Sierra Nevadas, a whole bunch of our coastal mountain ranges. Anywhere you see along a coastline that's a volcanic mountain range is a product of this process. These are the 3 ways that you can make melted magma. Questions about that? Cool. Good? Great. All right. All right, so now that we know how magma forms, let's talk about ways that magma changes. And it does change a lot over its time. So magma will actually change compositionally as time goes on. We call this Bowen's reaction series. For the longest time, everyone always assumed that a volcano that pushed out a certain type of, certain composition of lava had always done so and always would. Mafic always stays mafic. Felsic always stays felsic. A volcano that spits out mafic magma always will. We know different now because this guy Bowen, last century, did some experimentation, a lot of observation, collected a lot of data like good scientists do, and he realized, hey, the composition changes slightly as time goes on. Why is this volcano spitting out a different composition of magma now, or lava, if it's spitting it out, right, now than it did 10,000 years ago? What in general is going to be happening to my magma chamber over time? Is it going to be heating up or cooling down? Cooling down. Volcanoes do die, that is true, but also think of it scientifically, right? Not just historically. Think of it scientifically. It's near the surface, a heck of a lot nearer to the surface than it was when it was down in the mantle. And up here, we don't have as much temperature, so it is losing temperature. It's not as insulated. So it slowly loses temperature over time, which means that something's going to change. Do you remember I showed you in lecture 2 how I was showing you how the dark silicates form at high temperatures and the light silicates form at low temperatures? I said I was going to explain that today, and now I am. That is Bowen's reaction series, okay? As we lose temperature, certain minerals are going to form because they have certain crystallization points. The melting point of a mineral is also its crystallization point. If I'm heating a rock up, each mineral will melt at that point, and as I'm cooling that magma back down, each mineral will form at that temperature too. So if I'm cooling off a magma, olivine forms first. I get to form olivines. Olivines are rich in iron and magnesium. They're the first dark silicate that forms. The more olivines I form into solid crystals, the less irons and magnesiums are left in the magma. I am reducing the amount of iron and magnesium available in my magma as I make more olivines. Then as my temperature continues to decrease, I make pyroxenes. You know what else they use? Iron and magnesium. I'm pulling even more out. As time goes on, my magma becomes more and more depleted in iron and magnesium. And what does that do to its composition? Can I even call it a mafic magma anymore? Or an ultramafic? It always starts out ultramafic because it's from the mantle. I can't call it ultramafic anymore because the proportion of iron and magnesium to everything else has changed so much as I'm making olivines and pyroxenes. I now call it mafic. Time goes on, I make more olivines, more pyroxenes. Now I'm making amphiboles. Now I'm making certain types of feldspar. My composition continues to change slowly over time as those elements go from being in the magma to being in the crystals. So my magma composition goes from mafic now to intermediate. Now at intermediate, I'm making my biotite micas. Okay? I'm making my sodium-rich feldspar. More time goes by. Bowen's reaction series continues to work its magic. I go from intermediate to mafic, felsic. I'm making my potassium feldspar, muscovite mica, and finally, right at the end, my quartz. So by this, we know the same process happens to all magma chambers. It's not like there once was a mafic magma chamber that always was. Or this magma came from the mantle already felsic. It all starts ultramafic, the same composition as the mantle, And as time goes on, Bowen's reaction series has proven it gradually transitions to felsic before it dies, before it fully crystallizes.
So like every eruption is like pulling these chemicals out of the volcano?
Yeah, whenever you are expelling material from a magma chamber, it is going to be whatever the composition of the magma chamber at that point in time is, but different from the one it was before, and different from whatever the composition of the lava expelled from the next eruption will
So
be.
whenever we see a volcano making quartz, does that mean we know it's closer to dying?
So volcanoes don't really make quartz like that. It has to form in the lava that's expelled. But it'll be, if it's forming quartz, it'll be microus crystals, right? Because it's going to be extrusive at the surface. So it's not as useful a tool when we're talking about right now eruptions, recent ones or ongoing ones. Very useful for interpreting the past of many past volcanoes though. Okay? So today, right now, we are going to have a neat exercise. Chloe, would you mind handing out those bowls? This is what I call my M&M differentiation series. Where I have those papers. I think I have them over here. You are going to use these M&Ms and some paper magma chambers, which I am about to hand out. And you are going to see exactly how Bowen's reaction series works. I had you make 10. One of them is for you if you wanted to participate too. Or just eat M&Ms. Either way works. All right, there you go. All right, please do not eat your M&Ms until the exercise is over. Eat all of them. So the first time that I did this, 5 years ago, I bought like 10 cases of M&Ms from Sam's Club and spent like 4 days with my wife sorting them out by color. Ever since then, I have simply ordered the colors that I need from the M&M company, which is more expensive, but saves me lots of time sorting. So I prefer that method.
Oh, by the way, I sent you an email about why I was late.
That's okay, I got it.
Okay, good.
Yep. All right, camera, you following me? Yes, you are. Okay. Oh, Emma's coming back. I'll just wait for her. All right, we're just missing Adriel. We'll fill him in when he gets back. All right, we are doing Hart's M&M differentiation series. Okay. Again, please do not eat these until after we are done with the exercise. So everyone has in front of you and for those of you that are doing this online, I'm going to be doing the same. Ow. My magma chamber just cut me. Okay, I'm going to be doing the same thing here on the screen. You just don't get the benefit of eating M&Ms after the fact. Sorry. You can always go and buy yourself M&Ms. You know what? Pause the video right now and go buy yourself M&Ms. Then you can do this with us. Okay? All right, so you have a magma chamber on this piece of paper. We are going to be forming certain minerals. Your bowl represents the chemical composition of your magma chamber right now. Notice, stir it around a little bit. Tell me what the proportion of dark and light seems to be. Like iron and magnesium, which are purple and green, compared to, say, silica, which is orange, and your other light silicate forming elements, which are the yellows, blues, reds, etc. You have a little key down at the bottom that tells you what is what, by the way. Yeah. Can you guys see the brown M&Ms in there? Yeah? What's the proportion of the brown M&Ms to everything else? Is it pretty small? Yeah. Yeah. Those brown M&Ms, they represent everything else, all those rare elements. Right now, they are very diffused in amongst everything else. So our temperature is going to drop. We hit 1200 degrees Celsius. Go ahead and form an olivine. So 2 purples and an orange. By the way, oxygens are implied. If I had a color of M&M for oxygen and I put them in your bowls, you would need gigantic bowls to hold all those oxygens. So instead, oxygens are just implied here in this case. Okay? So 1 silicon, 2 magnesiums. And that's going to go right down here at the bottom of your magma chamber because that's where they fall. They're going to slowly settle down to the bottom of your magma chamber. Okay, next up, we have pyroxene. 1 iron, 2 silicons. And that's going to settle down right about on top of that olivine. We're still forming olivines at the same time here, mind you. It's just now that we have dropped in some temperature, we are also forming pyroxenes. Okay, so now what has happened to your magma chamber? You have removed some magnesiums and irons. You've also removed some silicons. But the proportion of iron and magnesium you have removed is much higher than the proportion of silicon you've removed. So you are slowly depleting your remaining magma in iron and magnesium. We can no longer call it an ultramafic magma. It's now moved more into the mafic category. We are going to make some amphiboles. So that's going to be 1, 2, 3, 4, 5 irons. And 1, 2, 3, 4, 5, 6, 7, 8 silicons. And 1, 2, yellow, which should be calcium? Yeah, calcium. Do you have a lot of irons and magnesiums left? No, not compared to everything else, right? Oh, those are yellow, calcium. Okay, then we've got calcium feldspar. So we're going to have 2 silicons, a calcium, and 2 aluminum. Blue. I could do a whole social exercise by observing how many of you are making neat, meticulous lines with your M&Ms and how many of you are just making piles of them. And then just decided to do piles. I mean, that probably also is telling in some way. Luckily, I'm not a psychologist, so I don't care enough to do such a social exercise. I'm sure it says something. I just don't know what. Okay. Then we've got potassium feldspar. We have now entered the intermediate zone. Okay? So we have 3 silicons, an aluminum, and a potassium. We are not making any olivines anymore. We're barely making any, if any at all, pyroxenes, amphiboles, and feldspars. That's pretty much the name of the game now. There is not enough iron and magnesium left to make the other ones. And what iron and magnesiums are left are going to go into the biotite that forms here in our intermediate phase. So we've got 3 magnesiums, 3 silicons, a potassium, and an aluminum for our biotite. Okay, well, how's our magma chamber looking? Pretty depleted in the heavy stuff. Pretty high in the light stuff. But overall, looking kind of empty. Right? We're approaching the end here. After we start forming biotite, we leave behind the intermediate phase, and we have entered our mafic phase, and we are going to form muscovite. 6 silicons, 2 potassiums, 2 aluminums. We're pretty low in temperature now. We're about 400 degrees Celsius. We've gone from 1200 degrees Celsius to 400 degrees Celsius. We've lost a lot of temperature. We've lost a lot of energy. We've lost pretty much all our iron and magnesium, right? Just not much left there. We've lost a lot of our other elements. But what are we still high in? What is the element that you still have the most of? Silicon. What is the mineral that's going to form out of just pure silicon? Silicon and oxygen. Begin. The oxygens are implied here. Mineral. Remember, that forms at the surface. We're talking about what's happening in our magma chamber. What's going to form in our magma chamber out of pure silicon? You ready for this? All right. It's probably the worst one of all of these. Boop. Quartz. 1 silicon. Quartz is just SiO2. 1 silicon, 2 oxygens in a 3-dimensional framework. 1 silicon, that is your quartz. Okay. Here we are. The butt end of the life of this magma chamber. It's lost so much stuff. What's left, though? Here, show me your magma chamber. What do we got? What do we got left in the chamber here? A few potassiums, a few aluminums, some silicon, sure. Okay. You see those brown ones? Is it a lot easier to see those? Those 2 brown ones in this whole bowl that you got? What is the proportion of these other rarer elements to everything else now? A heck of a lot higher than it was at the beginning. And this, my friends, is where pegmatites come in. So here you can see we've got our ultramafic phase, our mafic phase, our intermediate phase, our felsic phase. Right here at the very end, as our magma chamber is finishing off, we are going to get our pegmatites. And our pegmatites are going to be rich in those other rare elements because guess what? They've got nowhere else to go. They have to bond with something now. They didn't want to this whole time. Now they don't have a choice. So they bond with something right there at the end, and that is what makes our extremely valuable mining targets that are pegmatites. Okay. Any questions about Bowen's reaction series? How this works? Straightforward? Did the M&Ms make it easier? Good. You may now eat your M&Ms. Thank you for your patience. Okay. So there are some things that can kind of get in the way of Bowen's reaction series. Some things that can interfere, to say, kind of put it this way. So our basic general Bowen's reaction series is going to work with our fresh new magma body. It's going to spit lava out. It's going to slowly cool off. As it cools off, it loses certain elements. Those first minerals are deposited around it. By the end, we have gone from, a mafic magma to a felsic magma, and here we are. But some things that can happen to interrupt that. Assimilation. What is that magma doing to the rock around it? Yeah, this magma is really hot, and it's not saying, excuse me, would you mind just getting out of the way? I got to kind of push through here, right? It's not a line at the mall. It's rock, and it's melting through it. And where is that melted rock going? Into the magma, which in turn is going to affect the chemistry of that magma. So if I have a mafic magma that is melting its way up through felsic rock, what's the overall chemistry of my magma going to change toward? Mafic magma, felsic rock getting melted into it. We're going to meet up at intermediate. And this is why so many mountains on continents are made out of intermediate igneous rock.
So when it's like the new rock, even though it's still melting towards it, it's still going to be the mafic because it doesn't have enough to consider intermediate? Enough felsic?
Depending on the proportion of felsic or intermediate rock it's assimilating into it will determine how intermediate it becomes. What about if I have a magma chamber rising through oceanic crust? Is it going to come across any felsic material? No, not really, which means that we're still going to get mafic material at the surface. And this is part of the reason why I said the most commonly expressed, like expelled, igneous material at the surface is basalt. Is that extrusive mafic material. Why? Most of our Earth's surface is covered in ocean crust, which means that most of the mantle that comes, most of the magma that comes to the surface is under the ocean, which means it never encounters felsic material, which means that it comes out mafic. Whereas that which comes out under a continent is going to gradually become more intermediate and then more felsic. Oh, we just tied up those ideas together. Great. We've answered some of the most important questions of life today. Okay, or at least of the class. All right. Something else that can happen, magma mixing. We have our magma chamber, which, may have gone through a portion of its life cycle. Maybe we're about to enter the felsic phase. And then a brand new magma chamber rises up beneath it. Nice, fresh-faced, mafic magma. Slides right into that one, and they mix together and kind of refresh the magma from that one. And now we're a lot closer to mafic than we were before. Basically resetting Bowen's reaction series. Going back in time for that magma, more or less, because we've just introduced more mafic material to it. All right, this idea of partial melting that I talked about earlier. Some minerals will melt before others. It's not a strange idea. Here are some other materials that do the same thing. On this tray, we have linseed oil. Okay, here's our linseed oil. Then we have water in the form of ice. We have chocolate. As you increase the temperature on this tray, we're going to go from negative 25 Fahrenheit, or excuse me, negative 25 Celsius. We're moving up. The linseed oil starts to melt basically immediately. Think of that as your quartz. Quartz has the lowest crystallization point and therefore the first melting point. You increase the temperature even more. Once you hit 0, water starts to melt. Okay? Think of that as more like your feldspar. About 800 to 1,000 degrees Celsius, it's going to start to melt too. Then you increase the temperature even more, and finally, your things with the highest melting point, like olivine and pyroxene, start to melt. Partial melting is the reason why you end up with things like porphyritic rocks, where you have the big crystals and the small crystals. Some things don't melt and get reincorporated into other rocks later on. When a body of magma, which I've just been calling a magma chamber up to this point, pushes up through the rock on the surface, we call that an intrusive body. There are several different types of intrusive body. Massive intrusive bodies and tabular intrusive bodies. So those are two things we differentiate them based on their shape. Massive intrusive bodies are kind of big blobby pockets, whereas tabular ones tend to follow linear directions, straight up through rock or cutting along the rock. When it cuts up through the rock, when it cuts perpendicular to the layers of rock around it, we call that a dike. Okay, so this is a dike slicing up through the layers of rock in this mountain right here. Perpendicular to the layers of rock around it. Not vertical, perpendicular. Okay, you understand the difference there? Vertical just means up, right? Up and down. Perpendicular means whatever's around it, it's cutting across it. Okay, a dike does that. Sills cut along those layers, not against them. They cut along them, okay? So this is a horizontal sill here. Doesn't necessarily have to be horizontal, but this one was, okay? And this is a perpendicular dike. The massive ones, we separate those into batholiths, which are really big magma bodies, typically larger than 100 kilometers square on their surface expression. And then about anything smaller than 100 square kilometers is called a stock. Okay, so this is what an underground version of one of those would look like, a magma chamber that we only see the top part of, but is down here as well, right, deep underground. When a sill or a dike separates from a batholith or a stock and makes a separate chamber off to the side that pushes the layers of rock above it upward, kind of shoves them upward as it's making space for itself. We call that a laccolith. Think of that as like a side chamber, so to speak. Okay? So these are your massive intrusive bodies.
So that's like the magma, like you do the rock down inside and then formed a deep pocket.
Yeah, it found a space where it could start storing magma somewhere off in the distance over there. Yeah, exactly. All right, and then finally, I'm just going to mention mineral resources. We get a lot of mineral resources from igneous rock, especially those pegmatites I mentioned earlier, okay? Those pegmatites are very, very important. We get uranium and rare earth elements. Rare earth elements are a lot of these ones down here, okay? The lanthanide series and the actinide series, okay? We get a lot of those from places like pegmatites. And those are materials that we need for really anything that has complex electronics. Everything from a laptop to a smartphone, an Xbox, the military Tomahawk missiles, X-ray goggles, supercomputers, oh goodness, AI servers, right? Needs these rare earth elements. Small quantities of them, sure, but it still needs them. So whenever we find a pegmatite, that's a great place to look for these things. Especially considering right now, you know who owns most of the market on rare earth metals? China. Huh, yeah, China. They own estimated somewhere between 90 and 95% of the world market on rare earth elements right now. And anytime anyone else, especially the US, tries to open a rare earth element mine, they drop the price on rare earth elements so that it's no longer economical to start the mine. There's a place in California that I think I heard they tried to start that mine like 3 different times over the last couple of decades. I want to say like 50 years or so. And it would cost them like $15 billion or something to start this mine because of how complicated the process is. And every time they try, the market keeps fluctuating because people mess with it so that they can't. China's got everyone real good with that one, don't they? And in many other ways too, but that's just one way. The way that we can get a lot of these elements, in particular gold, this is a vein of gold running through some igneous rock. I used to work at a gold mine, I think I mentioned that, in Nevada. And what we would do is we would hunt for hydrothermal deposits. Basically what happens here is as the magma chamber is cooling off, it's still hot enough that it heats the rock, the water and the rock around it up, and that really hot water dissolves out soluble, so dissolvable metals from the igneous rock. Gold, silver, uranium, lithium, a lot of these metals that can easily dissolve in water will dissolve in this really hot water, and as that water flows away downhill in the rock, it's going to carry those dissolved metals with it. So my job at this mine was to basically track where these hydrothermal solutions went. We would drill holes a couple 100 feet deep, study the samples at depth, the depth we're looking at, and figure out what path that water took until it cooled off enough that the gold settled out. And then we would build a mine wherever we figured out that the gold landed underground. So, resources, very important, lots of them in igneous rocks. Any questions about today's lecture? No? I'm not going to give you Lab 2. I'll give you Lab 2 on Thursday. I'll leave the rest of today's session to continue working on Lab 1. Okay? I will end the recording here. If any of my online students have questions, feel free to leave them here in GoReact or send me an email. Please do not use Blackboard Messenger. Again, I don't really see those consistently. Please use email, or for my online students, you can also use GoReact. Thank you.